Okay, so I will present the work that I do and that we do at CESBIO, because we are a small team related to Vietnam in general and Southeast Asia as well. So I prepared quite a lot of things, so maybe it will be too much, I don't know. But in any case, if you have questions, you don't hesitate to ask in the middle as well. Okay. So the main scientific topics that we cover are these ones. So we monitor and we want to monitor and understand the changes in agroecosystems. So with a focus on rice fields and on forests, and linked to the carbon cycle and water cycle. So deforestation, emission of methane from the rice fields, look at irrigations, floods, droughts, and so on. And the main tools that we use for these are remote sensing, and especially radar. So we also call it SAR, remote sensing, because it's adapted to cloud-prone regions. And we also use a bit of modeling, but not at all the same kind of modeling that you do here. So maybe we'll talk about this. Okay, just a short summary of why we are working in Vietnam. So we have, well, historically, we had a few activities with punctual visits of Vietnamese postdocs and researchers, but we have intensified these activities since about 10 years because of a conjunction of things. So we have had activities with USTH, teaching and research. We have had a project funded by ESA called GeoRice on rice monitoring, and also other projects by CNES. I will. ESA yes. European Space Agency. Yes, it's like NASA but for Europe. And so the staff we have, so Thuy Letoan is really the key resource, the person who really initiated all these works. So she's originally Vietnamese, but she's lived in France for maybe 50 years or even more. And she works at CESBIO, and now she works with CESBIO, which is a startup created at CESBIO. And there's myself, there's Tao Nguyen, who just started a PhD in October. We have one person from CNES, so the French Space Agency, Thierry, so who's helping a lot on all the things like processing chains and so on. There's a researcher, IRD researcher, Sylvain Mangiarotti, who is more on multi-domain dynamic modeling, so modeling of chaos and very mathematical stuff.
He came here to make it.
He came.
Well, not in the lab, but it was kind of IRD influence.
Oh yeah, I know that. 2 years ago?
I know it was at the French.
Yeah. Was it last year?
Last year at the French.
Yeah, he had.
When we had all the animations with the one camera, he was one of the presenters, and I think he gave a seminar the day before at the French Institute on chaos modeling.
Okay, we have other PhDs. Hua, she's not with us anymore, but we still have contacts. And
Where is she?
She's still in Toulouse, but in a small startup, Carbon Farm. And then I want to mention Stéphane, who worked at CESBIO for many years, but now he funded Globeo, which is a startup, and we still have a very close contacts with him. Yeah. So the partners that we have in Vietnam, main partners are VNSC in Hanoi and Ho Chi Minh City, also USTH and a little bit HUST so far, and we try to have to involve as well users and the public sector. So we have had contacts with agencies from the ministries, the MARD and MONRE, mostly within projects. And then we also have a few activities with the neighboring countries, so Thailand, Laos, and Cambodia.
Masqué, we don't go to
Okay, so we have quite a lot of projects. So related to RIFE, we have a it's called VIETSCO 2. So the SCO is a Space Climate Observatory. So it's a big project led by CNES, and they fund a small project within this big project. So we have one funding from this linked to the Mekong Delta, so adaptation and mitigation to climate change and so on. We have Star Farm, so we don't need to present it, I think.
Very famous.
Yes. So we have submitted also a project to, again, an ESA call, but I think we might not have this one, I'm not sure. So that's for rice. For forests, another SCO project, it's called TropiSCO. It aims at estimating forest loss over the tropics, and I will talk about this a bit later. And then we have activities on biomass. So biomass is above ground biomass, so it's the carbon stored in forests. So we have this project who produces biomass maps every year, and our role in this project is to assess these maps and the changes, and especially in Southeast Asia. And then I have another project which is starting very soon. It's not in Vietnam, it's in northern Laos, but it's related to land use mapping and wetland mapping. It's also quite relevant. Okay, so I understand that most of you are not very familiar with remote sensing, so I just prepared just a few slides to introduce the main concepts and why radar. So we have basically two kinds of categories of sensors, passive and active sensors. So the passive sensors are the sensors who record radiation, which is emitted naturally by the Earth, or which is reflected by the Earth. So for example, well, the typical example is the optical sensors. So you might know Landsat and these kind of things. So it's exactly like a camera. Like you take a picture and you record the light that comes from the Earth, which is actually the light of the sun reflected on the Earth. So obviously you cannot have acquisition at night. And if it's cloudy, you get a picture of the clouds. Very interesting. So the active sensors, on the other hand, are the sensors that send their own source of radiation. It can be microwave or light. Light, in the case of LiDAR, it's a laser. It sends a light and records what comes back. And the radar, synthetic aperture radar, it's a microwave. So you can have day and night acquisitions. And in the case of microwave, so radar, you can see through the clouds. So that's one example over Hanoi. On the left, you have a Sentinel-1, which is a radar, and Sentinel-2, which is an optical sensor. So you can see that you get different different informations. Actually, you do not see exactly the same thing, the same structures, and so on. So it's quite complementary. Here you see a bit of clouds. So there's not too much clouds because it's February, it's the dry season.
Usually it's a little bit more cloudy.
Yeah, it's one of the few images that I could find.
Actually,
if you take one now,
today is to find an image without.
That's okay. And so the principle of star imaging, you have a radar on board the satellite. It sends an electromagnetic wave towards the Earth. The wave will interact with the target for us. So part of the wave will go in several directions, and we record the part of the wave that comes back. And the normalized ratio of the received to emitted energy, that's what we measure. It's called the backscattering coefficient. So it's a pixel. So we make images with this, and each pixel has a backscattering coefficient. The main sensors that we use, so there are many stars in space, but most of them are commercial, and we have to pay for this. So for science applications, we prefer to take free data. So we use, I did not mention, but the SARs, they can work at different frequencies, so different wavelengths. and we will measure different things. So this one on the top, Pulsar and Pulsar 2, it's L-band. So it's a wavelength of 30 centimeters, launched by Japan. And they produce global mosaics at an annual scale. So every year, a mosaic. So you have actually one image every year at 25 meters. And Sentinel-1, it was launched by ESA almost 10 years ago. And this one was really a game changer, like for SAR applications, like a big revolution, because for the first time we get images, systematic acquisitions every 12 days, 6 to 12 days. And it's available for free. And so it has really triggered a lot of applications.
What does this mean, the gradients on the image?
On the image here, it means, well, the image is a composite of, well, I did not mention as well, but in SAR, you measure in different polarizations. Well, in the case of Pulsar, you send a wave that is that has an horizontal polarization, and you measure back horizontal and vertical. So you have HH and HV. And so we make an image of this. Well, we use the two polarizations to make false color. And so the gradients here, more or less, it's related to the amount of vegetation. It's not only this, but mostly. So in the desert, you have the blue color, and if you go to the dense forest, you have the very bright green here.
So I have a question about this. When you say that they produce an annual image, that's it means how long does it take for one satellite or those satellites they launch to cover the whole world?
To cover the whole world, it takes one full cycle. So it's, well, I think in the case of Pulsar 2, it's 24 days. So it means that they don't distribute all the data that they just make a mosaic.
So when you say pay for those images, they will one image later?
For this, we don't pay, it's for free. But if you want data every 24 days, you have to order and to pay for this one, not for this one. Okay, so now I will show a few results. So first on forests. So this was an example of the work done by my colleagues on detection of forest loss and regrowth using these annual mosaics of Pulsar from 2007 to 2010. So it was quite interesting because we have a full view, but we don't have it's not near real time because it's every year. And then when Sentinel-1 was launched, we wanted to use it to do the same thing, but in near real time. And so if the basic idea is to use the time series. So we take one pixel and we look at the evolution of the backscattering coefficient. Here in black, you see it's a mature forest, for example. But it's actually in this area, it's plantations, rubber plantations in the south of Vietnam. So the black curve, you see it's more or less constant at high values, and the blue, red, and green curves, they show parts of the plantations that were cut. So we have a decrease in the backscatter, and we detect this decrease and to detect the forest loss. So that was a very simple approach that we developed at the beginning, and then after some time we found out that it's not that simple actually. So we developed other indicators, more complex, and we really improved a lot the method.
So you say that logging 1, logging 2, and 3 is related to raw fields or remote position?
Logging 1, 2, 3,
yeah.
It's different fields, well, different parcels, different plots, yeah, which are cut here at different dates. So this one is cut at this date, this one a bit later.
It's mostly related to the habits?
Yes, it's because for in the case of rubber plantations, they harvest well, they cut the trees every maybe 15 years because they are not productive anymore, and they're replaced by new trees. Okay. And so based on this kind of approach, we have launched the Tropisco project, which aims at doing all these detections on the whole tropics in real time. So for the moment, we have only a few test sites. And one of these test sites is this area, Vietnam, Laos, and Cambodia.
When you're speaking about test sites, it's because it's the whole country and
it's the whole country, but because we want to do the whole tropics, so we started with just a few countries. Because it takes a lot of
because that's what I was thinking
yeah,
about.
yeah, sure. No, it's a more like demo site, or because it takes a lot of resources to process all the data. So I don't know, maybe we can, so there is this website where we have all the data and there's a web GIS and so on. So maybe later I can show you this website. And so based on these detections, we can look at the monthly forest loss rates in the 3 countries. And so we see that there's a clear seasonal pattern because they cut the forest mostly in the dry seasons. In the wet season, it's more complicated. And so what's interesting to see is the trends between years. So there's a marked decrease in 2021 compared to the previous years. And
so yeah, it means in terms of surface. So of course, maybe there is not a clear correspondence with the number of trees, but in terms of surface, it means that now every year they love 3 times what Vietnam and Cambodia love together.
yes.
Oh.
I will show now the website.
Yeah, it's really impressive.
Actually, it's because so you see, you can zoom in and you can quite clearly see the border between Laos and this is because this was not true in like 10 or 20 years ago. If you look at the past map, you see that it was almost the same rates. But then Vietnam joined the RED initiative. It's RED is reducing emissions from deforestation and degradation. So it's a big initiative. And so they reduced a lot. But part of the deforestation actually migrated to Laos because there is still the same needs. So it's actually there are a lot of trucks from Vietnam who take the wood and take it back to Laos to Vietnam.
Yeah, that's really, really impressive.
So you can do like a animation.
We don't know at what rate Laos can sustain this.
There's some big company from Vietnam take the wood from Laos to the land.
It's like the sand in Cambodia.
Hoàng Anh Gia Lai is Hoàng Anh Gia Lai. Yeah, one of the
So yes, that's it for us. And we also, as I mentioned, we also look at biomass change and try to relate the observed biomass change from satellites to the observed forest loss. Try to see if it's consistent. And this was a field trip that we did in Cambodia last February. For those who know her, this is a tree here, still going in the field. Okay, so I put a few research questions that are like the points that I'd like to investigate a bit further in the next months and years. So now that we have this Tropisco platform, we So I'm quite interested to look at to analyze the trends of forest loss and biomass change in the last years, and especially to link it with well, external factors, economy, COVID. We see that COVID had quite a strong impact on the reduction of forest loss in some areas, linked with forest policies, so REDD+, and so on. And also the forest biomass. So we produce a lot of biomass maps, but actually we are not very confident in these estimations because we don't have a lot of in situ data from Southeast Asia. So how to improve these estimates, and I'd like to know a bit more if people in Vietnam are measuring biomass in the field and so on. So to address this question of what is the carbon budget of forest. Okay, that was for forest. And now a lot of my activities are also on rice monitoring. So the context is the Mekong Delta, which is a very threatened agroecosystem. Climate change is expected to be quite severe in these areas with changes of precipitations, temperatures, increase in extreme events, typhoons, droughts, floods, and the sea level rise will increase the vulnerability to salt intrusion. The salt goes inside the Mekong Delta, and you cannot grow rice when it's too salty. And although the climate change is exacerbated by human activities, in addition to sea level rise, there is subsidence. So the land goes down by 2 to 4 centimeters per year because of groundwater extraction, mostly urban development. And so it increases the risk of submersion, coastal erosion, and changes in the Mekong discharge. So you decrease the rate of sediments, and so you decrease also the fertility of the delta. And so on intensive agriculture, and also we have greenhouse gases emissions from the rice field, so methane mostly. Okay, methane is Mekong Delta. It produces half of the rice in Vietnam, so it's a very important region. It has a lot of people, 20 million inhabitants, and 90% of the delta is below 1 meter above sea level. So it's very vulnerable. And there's a high risk of submersion and of big parts of the delta in the future. Okay, so for rice monitoring, we again use the Sentinel-1 time series. So here I just put a color composite of Sentinel-1. So it's 2023, not 203. So it's 3 images of January, March, and June, which are put in the red, green, and blue channel. So actually, most of the colorful things are rice fields. So they appear in different colors because they are at different growing stages. So you see that there's quite a lot of information in this time series. It's not all black and white images. So well, basically the method is analysis of time series. So here I have put some time series of different kinds of land use classes. So the red thing is rice field. And so in the Mekong Delta, farmers grow 2 to 3 crops of rice per year. So all year long they grow, and so on. So here we can see that the one rice crop is marked by well, there is some time where the backscatter is very low, which corresponds to the flooding at the beginning of the season, and then the rice grows and the backscatter grows as well, and there's a very dynamic behavior. And if you compare to other land use classes, so we have plantations, coconuts, villages, and waters. These are very much more stable in time. So the idea to detect the rice is to look at the backscatter increase, which is more than 5 dB, which is quite a lot.
Yeah, sorry. Well, maybe I'm the only one, but what is backscatter?
So the backscatter is the pixel values in the radar image. It's what we measure with the radar sensor. Yes.
On the water curve, what do they represent?
The peaks. So the water here, I took a polygon in the Mekong River. And the peaks, no, it's really in the middle of the water. Can you guess what the peaks are?
In the middle of the water.
It can occur anytime.
That's not true.
Yes, it's both. Yes,
Okay.
it's a boat.
Boats.
I can show
Okay,
again.
the boats.
No, a boat. Okay, it's this kind of image, and you see.
Because you take one
pixel.
So you have 1 pixel per minute.
You see, there's a lot of activities now in this river, and so the bright things, the colorful things, are the boats.
You don't have like any system for your data?
We could filter out, but we don't really need it.
Does that impact on your final conclusion?
No, it's not for the rice mapping. It has no impact because we create a water mask and then we mask out the water. Okay, yes, and also here I show 3 different configurations. So we have the triple crop rice on the top, double cropping rice. So we have, for example, here 1 crop here, 1 crop here, and then it's a wet season. So there's a seasonal flood all over the Mekong Delta. This is the backscatter in time. So what we measure from the satellite. So that's what we use to later to do a classification to know if it's triple or double.
What do you mean by the village? That's the location of the village, or?
And here in village, it was I took a polygon on a village, and so the buildings usually they have a high backscatter, higher than the rest, so, and quite stable because the village does not change.
Okay, so to be very clear on what you present here, actually the different curve here is the evolution in time of 1 pixel.
Yes. No. Well, in this case, it's a polygon. It's a ring. Yes.
But at least it's a very specific place.
Yes.
Very specific evolution.
Yeah, it's just
So
an
it doesn't
example.
represent the surface, so that's why when I saw the peaks water, I was thinking about flooding because I thought it was actually the aggregation of all the
No.
similar data, but no.
No, it's the evolution in time of the pixel.
So it's the mean of all pixels in the polygon,
Yes, in this case, yes.
but then on the peaks of the water curve. So there's 1 day, but there are boats everywhere.
No, it's not everywhere, but the boat will have a value. The boat, just the pixel of the boat would be here, maybe. And so if you average with the rest, you get a value like this.
Yeah, but I mean, on this specific day.
On this polygon.
On this
Yeah.
specific day, in that polygon, there was a lot
There was
of boats.
just one boat.
But the backscatter is the equivalent to 1 million. So even if you average with
Very low, those behind.
that's it. So this is not algorithms because not the surface of things, it's you determine the surface and then you measure things here. And basically, when you attribute something like water, village, blah, 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 it's because you know in situ where you know that it is a river, you know that it is a crop.
Yes. So this, yes. So this is just the analysis of the time series. But then when we do the classification, we try to find features, classification features derived from this time series to understand. For example, if we want to map the water class, we say that we take the average backscatter in 1 year, And if it's below -25, then it's water. That's just an example. So we have, so that's typical behavior of triple cropping rice, double cropping rice, and we can also see the changes in time, land use changes. For example, that was a rice field that was converted to aquaculture. So it was rice very variable and then very quite stable. So by using this time series information, we can have ideas of the changes that occur. And so based on this, we can create maps at each season of the extent of rice.
Okay, so sorry, I interrupt you.
Yeah, please.
Just to be sure, so you have previous diagrams where basically you are able to you classify yourself and you say, okay, this is water, this is what is the signature over the year, and then you use this signature to classify
Yes.
what you see.
So what I show here typically is the first things we do when we want to start a new application. We look at the time series to understand which rules we will put to classify.
And you don't take polygons randomly.
No, we select polygons
You know
that we know what is yes. And based on this, we put some rules, and then we take all the stack of images, and we take each pixel individually and look at the time series and classify.
Yeah, make a clustering and classify.
So that's an example of one season of rice, and so we can get the extent of rice during that season. And what's interesting is that we get the results directly in the middle or at the end of the season, while if you want to get the data from the national or local statistics, you have to wait sometimes 1 year. So it's more quick. We can also estimate the phenological stage, so the growth stage of the rice at each date. So we get the sowing date from the satellite, and then we look and the phenological stage is an important feature for some models, production models, and so on. We can look at for example, here the impact of El Nino. So in this season, 2016, it was quite a strong El Nino with a lot of drought and salt intrusion, and we see that in the coastal areas, compared to the previous year, we have a reduction of the rice fields. Rice is in red, and this is reflected also in the provincial statistics. So there's this decrease, except that we detect it 1 year before. And then what we also look at the impact of salt intrusion. So we worked with people who have made predictions of salt intrusion on different scenarios, different climate scenarios. And we cross this information with the current rice distribution to look at the area of rice which will be lost in the future, in 2030, 50, or whatever, based on the different scenarios. So for example, in this scenario, that's the projected loss of rice for the dry season in 2050 compared to now. All these regions cannot be cultivated as rice because it's too salty. So it's really scenarios and predictions. And we do the same for submersion. So because of the sea level rise and subsidence, parts of the delta will be under the water if nothing is done, if no dike is built, etc. And so we took again some subsidence scenarios. So it's based on groundwater extraction scenarios. So in the middle, if the scenario linked to a stable extraction, so same extraction as now, less extraction, more extractions, so more subsidence, and climate scenarios, so which reflect to the sea level rise of 25 centimeters or 60 centimeters. And based on these, we looked at the current rise areas which will be underwater. So that's the green areas. And we estimate that in 2050, that's between 22 and 58% of the rice fields that will be that could be underwater.
What type of model are you using for the prediction? I can understand that you data for the current situation and the evolution from the past, but
yes.
the future.
So for the future, so the climate scenarios is scenarios from IPCC, and
But you have a learning and you have a machine learning. We are using machine learning tools to predict.
no, this so it's based on scenarios, so it's
Just level of this.
It's a very mechanistic model.
yes,
If you have more than
it's related to the emissions, greenhouse gas emissions.
Just almost make the link between the
the rules, it's about the salinity of the soil and above the certain threshold. Then
Yes, for salt, it's above
Yeah.
a certain value.
And I have a question, but when you say the effect, for example, of any node, you see the previous MS and you see the MS during the time of any node. But how do you know and how much of the effect that rely on the any node and how much of the other effect like human activity, so that you can verify.
Well, we expect that there's not much other effects. I mean,
You assume or
we assume and we expect. From one year to the other, usually but there can be I mean there are changes like
because for example,
policy driven.
you know about the big change of human activity and behavior of animals, for example. Maybe it can be more clear what is the exact.
Yeah, no, that's right.
But in Vietnam, you say that we all blame on climate change and humans have no fault.
Yeah. No, but also there are incentives to convert from, well, especially in the coastal areas, to convert from rice to other activities and so on. But it's adaptation actually. Okay, and these results were presented in these reports from the GEMS project. I've seen some of these reports here.
Do you want to?
Maybe I have the PDF. But okay, and just a few words on the modeling that we do. It's also we are not modeling experts, but we try to use some models. One of the models is for the yield estimation. So it's called the HORIZA model. So basically the inputs of the models are weather data. So you put the temperature, rainfall, soil data, information on the variety, the rice variety that is used, information on the crop management. So is it irrigated, flooded, and so on. And the model will simulate the yield based on this information, but you can also put some inputs from remote sensing. So if you put the date of sowing, the observed date of sowing, observed plant height derived from radar and so on, you can really increase the accuracy of the simulations. And you can use this model as well to project the future yields under different climate change scenarios.
You know what's behind this model? I mean, is it kind of cellular automata?
It's also